Hello and welcome to 2D Modelling 101 webinar. Thank you everyone for joining up. My name is Ben Anderson and I head up the licensing here at XP Solutions, and with me here today is Chris Huxley, our resident 2D modelling expert. So if you do have any questions from today's webinar, you can email us at apaceducation@xpsolutions.com. We don't leave any questions unanswered here at XP. So if you're going through this presentation and you have some burning question, by all means reach out and we're happy to assist you in any way that we can. So just a little bit about XP. For those who don't know XP, we are predominantly a software house for stormwater modelling software. Now I work with a lot of practicing engineers, and I'd say the thing that is the most unique in the market based on what they would say is our integrated hydrological 1D and 2D all in the one program. So you don't have to go between different software packages when you use XP. It's all just in the one package designed to get the results that you'd need as a hydraulics or flood modelling engineer. We interface with all of the standard engineering packages out there. A key advantage is our integration with 12D. You can bring in your 12D tins. Likewise with your Civil 3D, AutoCAD, GIS. We're compatible with all of those tools, bringing data in and out of those packages. Another big thing that people like is our really powerful 1D engine. This allows you to model and design a detention basin whilst integrating with a 2D overland flow. The routines in our 1D engine are probably some of the best in the market, and that'll help get your detention basin down nice and small using our optimization routines, and then linking that all together with your hydrology and your 2D means you've got a package that does what you would expect it to when modelling the real world. And then when you've finished all of that, your reports come out really easy. You don't need to manipulate data to make it easy to understand. It's generically quite available for you to just export anything you'd need to go straight into a report, including graphs, tables, long sections, even animations and videos. And we'll go through a few of those other options in the webinar. So that's enough about us. I think we'll walk into basically what we're going to go through today for everyone. So just a bit of an overview. So in terms of 2D modelling, we want to understand the future. So we want to understand today, and to understand that we need to know a little bit about the past in terms of 1D modelling. Why are we doing 2D modelling today? So we'll quickly go through some of that just to give some background. Why 2D modelling in terms of what are the benefits of it? Why should you stop doing what you're doing today to use 2D modelling? Some of the data requirements, you'll be quite surprised how few data requirements there are for a 2D model. I was quite surprised when I learned. I think there's only 4 things or 5 things you need for a 2D model, to get it going. So we'll go through those data requirements and where to find that data if you don't know where to find it. And then this is a really good one. We'll go through, if you've never done a 2D model in your life, you can start from the beginning all the way to the end and you'll have your first 2D model set up. So we've actually provided, which is a bit unique, we've provided the modelling data, and we'll be sending that out so you can go through an evaluation version of our software, open it up and play with the data and go through the steps that we're showing you today. Don't worry about writing anything down. We will send the recording and the slides out with that, so you don't need to frantically write notes. And this is the really good one. We'll show some tips at the end. So if you're brand new at 2D modelling, you don't want to make those little rookie mistakes. So we've worked with a lot of people. We train people who've never done this stuff before quite a lot. We know what people usually do. That's incorrect when you begin. So we'll just give you a step up so you don't make those little mistakes, and then question and answers at the end. So thanks, guys. I hope you enjoy the webinar. I'll hand over to Chris now, and he'll go through 2D modelling for everyone.
Thank you very much, Ben. Thanks for the introduction. So when we're talking about 2D modelling, it's very good to, I guess, look back at where we've come from. And hydraulic modelling in general actually goes all the way back to the 1960s. When back in those days, all the models were 1D in nature. So you had a 1D river reach, storage nodes, and branched networks representing catchments and rivers and pipe networks. The reason that those models were 1D in nature is primarily due to the limitations in computing power. So those are the days of large computers taking up whole rooms, even through the early days of desktop computing. So that the computing power requirements of 2D was too intensive for the computers back in those days. Moving forward through to the 1980s, 1990s, the computing power started to increase, and with that 2D modelling investigations began. Primarily, however, because of data limitations in terms of getting good wide coverage of topographic surfaces, and also still the limited computing power that was available, most of those studies were relatively small in nature and nested within larger 1D network models. From the 2000s through to the present, a lot has happened. So computing power again has improved. You know, those who are familiar with Moore's law would know that the growth in computing has been huge. But in addition to that, data availability has become, well, the availability has improved, but it's also become much cheaper to get. So it puts us in a very good position now to really capitalise on both of those advancements in terms of our assessments. So now we have a functioning framework within XP Swim where we can model our floodplains using a 2D regime or structure. That can be dynamically linked to 1D river channels, underground pipe networks. You can also link 1D culverts through embankments. And for the really advanced models out there, there's even multiple 2D domain functions where you can have varying grid sizes in different portions of your domain. So it's become a very powerful tool. And in terms of usability, traditionally the models, I guess, were used as either regional catchment models in a 2D sense, and in a 1D sense more of your urban network drainage models. They've now combined, so going from that regional approach and the detailed approach, we can now apply that within the urban environment and everything in between. And there's a number of benefits to this. So typically people focus on what type of model you can develop. It goes beyond that though. It's more important to consider what can these models be used for. So in terms of applicability, we're now seeing people not only using these flood models for, say, design assessments or land use planning, we're also seeing them being used for evacuation assessments, large-scale feasibility studies, getting information on flood force and sedimentation characteristics. So it's very wide-ranging applications these days. In terms of the history of the engine, the 2D engine that XP uses, it has over a 30-year development history, so it's a very mature product. And with that, more so than some other software or newer software on the market, you know, it's tried, it's tested, it's been proven accurate, it's been benchmarked against numerous university studies. Actually, my very first university thesis was focusing on benchmarking the engine that is within XP. So it turns out that the engine is probably one of the fastest on the market and one of the most mature and does get accurate results regularly. Let's put some thought into why you do 2D modelling. Back in the late 80s, and this is a quote from Australian Rainfall and Runoff, which was the primary guideline document in Australia. Back in the late 80s, it was considered that 2D modelling investigations were somewhat expensive, and there's a lot of truth to that. Back in those days, the data requirements were quite costly. That isn't the case anymore. Late last year, I did a survey in the lead up to the US, or the Californian Floodplain Management Association conference, where I spoke to 50 flood practitioners and asked them to rate 1D versus 2D modelling based on user effort, so the time it takes to undertake a study, and also the accuracy of the results. And so on the y-axis on the graph that we're seeing here, you can see that moving up the scale is increased effort in terms of time, and moving across the x-axis to the right, improved accuracy. So in many catchments, and this is more suited to overland flow, I guess, 2D modelling is more accurate and it's much quicker. There are still some very valid uses for 1D, so I'm not saying that 2D is the only answer, that there is always a need for engineering judgment when it comes about when you're designing your models. But in a broad sense, you know, it is typically more accurate and easier to develop a model. So just a very quick background as to the behind-the-scenes calculations for 2D modelling. What you're seeing here is a 2D mesh. It's a collection of cells that represent the area of interest. And within each of these cells, we're having water volume, flow velocity, and then also flow storage calculations being done. So if you do a quick comparison between the more traditional reach or 1D reach models versus a 2D model, the overall number of calculations in a 1D model typically varies from 100 to a few thousand calculation points, whereas in comparison, a 2D model with this cell configuration will have from, it's common to have anything from 10,000 up into the million calculation points. Actually, these days it's not uncommon to have up around 5 million or so. Now, in terms of accuracy, there's also some considerations, some things to take into consideration regarding the equations that underpin the actual solution schemes. So on the left-hand side here, there's a brief presentation of the 1D equations. On the right-hand side, we've got the 2D equations for the XP engine. You'll see that there's more terms in the 2D solution scheme. So in particular, we've got items in there for, say, the Coriolis effect or eddy viscosity. Eddy viscosity actually is a very important one, which simply isn't captured in the 1D solution. And actually some other 2D schemes don't capture it either, but when we're dealing with significant gradients in flow, it's very important to get accurate results, and that's where the maturity of our product really comes into play, where we've gone through the testing over 30 years to define what's important to get you accurate results. In terms of why 2D modelling is easier in some instances, the basic justification of that is that now we have good topographic data and easily obtainable and cheap data. It means that that's the underlying basis of all our 2D models. When you put the water on the model, it then routes those flows for you. By comparison, in a 1D model, that definition is largely left to the judgment of the modeler. In this animation here, we're looking at a levee bridge scenario through a township, and you can see the development of the preferential flow paths through the streets. You can see where the buildings are retarding the flow. This would be near impossible using a 1D model. But in 2D, I developed this model in the space of 3 days for an American authority. In terms of practical applications, so it's very useful for floodplain planning. Most agencies will have a 2D model these days, which is often shared with consultants. So they'll have a 2D model that defines their planning considerations or their planning levels and regions where they deem development to be appropriate. And often they'll share those models with consultants so they can update them for their own fine-scale development assessments. We shouldn't forget also that 2D modelling doesn't have to cover a whole catchment. It's equally as applicable across a full catchment as it is across a small, say, 20-lot scale assessment.
You could even do a single lot. We've had clients who do, down to 5 centimetre levels in 2D to understand how much level is going to be if you've got a power station that's going to go there, for instance. So there is really no limits to the scale. As long as your data's there and the data's refined, it's applicable for all sorts of levels and scales. And usually council will provide this data to you for, understanding the boundary conditions of your little development that you're doing as an engineer or something similar. Yeah.
In terms of those smaller scale studies with the fine resolution, one of the limiting constraints there is typically simulation time. So we'll talk about that later in the presentation. Okay, so data requirements. So we now know the history. Had a general discussion about the applications. What does it take to make a 2D model? Let's see. So typically we start with our surface data. And this can come from a variety of sources. Normally you'll start with your aerial LiDAR data, so it's aeroplane survey data.
Yeah.
And then you'll supplement that data set with, say, bathymetry or land survey. Now, land survey is, so that the LiDAR data is readily available these days. In Queensland, where we're based at the moment, usually you'll approach the local agency, the councils, counties, or also the state departments to get a hold of that data set. In the United Kingdom, their Environment Agency has flown LiDAR for the entire country. So it's often very good to approach those state and local agencies for the data sets. A word of warning though, with LiDAR, we've found that often the data that's available for areas where there's standing water bodies can be somewhat inaccurate. The survey from the airplane typically can't penetrate too deep into the water, especially if it's murky. So if this is the case, then it's also worthwhile contacting your port authorities, transport departments to try and get bathymetry data sets, which can easily be merged into an XP model. And in addition, also contact your key overland transport departments, so your departments of rail, Department of Main Roads, to try and get their land survey data sets for roads and rail corridors. Very useful data sets, if nothing else, to benchmark that the LiDAR is correct. The next piece of information that's required is your land use information. So this is typically used to determine how vegetation changes throughout the catchment, because that in turn affects the flow characteristics and how free-flowing the water is, or how retarded it is, I guess.
So long grass versus short grass or concrete is going to have different...
Or even buildings.
Yeah, buildings.
And the other extreme. We're very fortunate these days that aerial photography is very easy to get, through Google, Bing. Local agencies, again, have often flown that they often capture the aerial photography at the same time as they capture the LiDAR data sets. And GIS and councils in Queensland, for example, may have already digitised these in the GIS layers that can be directly imported into XP. Okay, so the third data set is our boundary conditions. Now, boundary conditions represent where water is entering our model, and you need to get those volumes and those flows correct. So sources of information there are typically rainfall data sets. For Australia, the Bureau of Meteorology has done a great job in providing for those data sets for the full range of design events. And Ben, you mentioned that XP now offers a service to source that data.
Yeah, so your rainfall, we just need your coordinates and you can send them through to XP and you can get your rainfall data just generated for you based on the BOM website's IFD charts. So it's really quite simple and easy these days just to get your rainfall into the model however you want. So there's several different methods and we might touch on those when we go through the example. What sort of rainfall and how you want to bring it in, rainfall on grid or a traditional hydrological approach.
So the next piece of data there is your flow inputs. Those can either actually be calculated from the rainfall internally within the runoff module of XP, or alternatively there is also the function to enter it in manually. And finally, your tidal or your downstream tidal water levels. Most port authorities will have that information in terms of recordings. Otherwise, you can also just look up your standard tide charts to make conservative assumptions in terms of just setting a standard high water tidal boundary. And finally, and this is really an optional item. It's not necessary for all 2D models, but in some instances it may be required that 1D hydraulic items be added. So that includes features such as culverts, bridges or pipes. In regard to this, however, it's worthwhile just mentioning, or keeping in mind, I should say, that the size of these elements relative to the volume of flow is worthwhile considering. If, for example, we're dealing with a conveyance area which has 1,000 cubic feet per second or 1,000 cubic meters per second, placing a culvert in that scenario, or modelling a culvert as part of the floodplain there that was, say, 30 centimetres in diameter really isn't going to have any significant impact on the hydraulics, so you wouldn't bother putting that in. At the other end of the scale, if there's a bridge that has an opening which is 5, 10 metres wide, then you should definitely be including that in the model.
Yeah. And I mean, this is really useful for mitigation options. So if you want to know if this big pipe or this big pipe will work, which one do we need to fix the problem, it's good to have that integration with the 2D which you've got. So
you can also embed your open channels in there as well. So just a quick summary of the data requirements. It's much less than what most people think. So we start with the surface data, your topography data sets. Your boundary conditions, so it's your rainfall, your tidal water levels. Land use information, so that's your aerial photography. And then there's also that optional 1D hydraulic component. Once you have all of those data sets, the final piece of the puzzle is really just setting your simulation controls within XP, and then pressing go, let the model do its calculations, then just review the results. So it's much less complex than what most people would believe.
What that 4 mandatory steps and then you're away.
Yep.
So that's probably why we're doing it these days, because the computer does the work. So that's where that's why it's easier than what people think than 1D modelling. Depending on the study, of course.
Yeah, I mean, there still is a place for 1D modelling, but it's all about working smart, not hard.
Yeah, I'd say the hardest thing is getting this data right, making sure that it's correct, refined. But if you've got the data there, just bring it straight in, and then we'll show you what we're going to do in a minute to show you how quick it is.
We might as well get straight into it. So we'll go to the demo now, and here I'll just build a very simple 2D model, and this will be the exact same data set that's provided at the end of the webinar. When you first open up the XP interface, this is what you'll see, and it'll prompt you to either open a model or build a new one. So if you build a new model, the first thing it'll ask is what units are you working with, and be conscious of this, that all your units and also all the projection that these files use need to be consistent with these models. Predominantly today, I'll be introducing information from the layer window, which is highlighted here on the left. That's used to control which data sets are active when you're editing. And predominantly, they'll be focusing on the 2D model and topography items that are highlighted here. If you right-click on those, there's a variety of options available, so I'll be mentioning those as well. On the right-hand side of the interface, these are all the editing tools. So it's useful to become familiar with those. Let's start building a model. So the first thing that people typically do is import a background image. And you'll see that there's an option for that in the lower left-hand corner of the layer window. It will simply prompt you to load in a JPEG. In this instance, I've sourced the background information from, I think it was Bing Maps, using ArcGIS, which then automatically creates a world file which matches the projection of this model.
So it brings the coordinates in.
Yeah, exactly. So here we have our demonstration model area, a rural catchment. Next thing we'll start doing is we'll start loading the topography data. So this is the surface data that I mentioned earlier on. By clicking on the DTM, that stands for Digital Terrain Model, by clicking on that option, we'll use the DTM Builder to create our topography. In this instance, we'll import an Esri grid file, but there are other options. So you can also import XYZ data or also just GIS files.
Or your 12D10 or whatever you've got.
Yep. After it's loaded, the DTM creator will look like this. And then it's simply a matter of clicking Create DTM. That'll take some time. In this instance, it took a few minutes and then displayed our topography data set. So it's very simple, very intuitive. Having loaded that data set, now we start creating the extents and bounds of our model. So we make the grid extents editable, and we'll draw a polygon which highlights the bounds of our model. And XP then creates a grid mesh of that area. By double-clicking, by entering the property data set under grid extents, you can then have control over the cell size and also the time step. And there's a checkbox above the time step option that means you can overwrite the global value in this instance, which we'll use. So we've set the cell size to a value of 4. XP then.
But you can see the little green lines to bring
each of those as a cell.
Yeah.
Okay, so we have our broad domain. Now the next thing we do is define the areas of that region which we think will be active for our calculations. Now the reason we do this is we simply reduce the number of cells that need to be calculated, therefore we speed up our simulation times. So under 2D model, we'll add a new layer called active areas. We use the polygon tool to draw in the region that we think will be wet. And we can, usually this is an iterative process. You'll draw an area, you may find that you've drawn it too large and then you'll bring it down, or vice versa. So now we know what our model extents are. I'd like now to just touch on how you can build the topography in XP. So what we'll do is we'll add a ridge line for the various roads that are in our model. And the reason you do this is just to make sure that the cell elevations of those features accurately represent those elevations. So XP uses 9 points for each cell, and the elevation is associated with those. If, for example, they don't align exactly with the crest of a road, then it may not be picking up those hydraulics correctly, but you can force the model to use those elevations using break lines. So we've already created a break line layer, a ridge break line layer. Ridge means that it will raise the values. If it was the gully, it would lower them. And we'll just import a county data set for those roads. And in this instance, we'll be sourcing the elevation values from the DTM that we imported. Now that DTM uses a much finer resolution than what this model does. So the DTM, I think, had a 50 centimetre resolution, whereas our model that we've created uses a 4 metre resolution. So it'll now sample that finer resolution data to append to the break line for those roads. It's a very quick way to include those features in the model. Next, we have our land use data sets. So the user has control in terms of which land uses they specify, and you do this via the global data options. So once the global data menu is open, scroll down to 2D land use, add as many records as you require. So for example here we've added maintain grass, and by editing it you can actually specify the specific value for that land use. Here we've used a constant value, but there's also an option for the depth varying roughnesses for those who would like to use that methodology.
I mean, there's a lot of they've already populated in some of the templates there, so you don't have to recreate the wheel, but you check what's in there and use them.
Absolutely.
Yeah.
So now you can see the full listing that we have for this model: pasture, roads, buildings, watercourses, vegetation and maintained grass. Once you've updated that global data, it's worthwhile to set a global value across your entire model, and then you'll overwrite that with polygons or GIS files. So you set the global value via the job control, 2D model settings, and then under general there's an item there for default land use category. So we'll set that as pasture because that's the most common land use. And then we'll overwrite specific regions of our model with the other values that we specified, which are now available and viewable on the land use in the layer option on the left. You can do that either by drawing polygons like we did previously, or also importing files from GIS. So if the county or council already has that data set in GIS, it's worthwhile importing that rather than digitising it. So this is what our data set looks like now, having imported it. Okay, so we're getting through now. So we've already done the first two items. Now we're on to the third, which is our boundaries. And we'll start with the downstream boundary. There's two options here. One is a head flow boundary, which we'll be using, or alternatively a head time boundary, which is more like a tidal boundary. So you'll see I'm always going back to this 2D model item in the layer window. Something that XP has done very well is consolidating all these options into one location. So when you're building a 2D model, it's very intuitive as to which data set you should be adding. So here we're adding the head flow boundary. As a recommendation for new users, when you're defining these boundaries, I'd turn on the snap item, which is shown there, and snap your boundary to the active polygon that we defined. And that'll just avoid any recirculations that can cause instabilities. And it's also recommended that these lines be digitized perpendicular to flow to get it's the most stable configuration. So we'll draw a polyline, snap to that boundary.
So it'll just trace over automatically.
Yeah, that's right. So it traces and joins the same vertex locations as the polygon. Now if we select that, we're using a head flow boundary here, we define a slope phase. That's the water surface slope, and then XP will automatically calculate how much flow should be exiting the model at any time given the water level at that boundary. Now you can let it calculate that by just specifying a slope, or if you have a rating curve, you can enter that as well. If this was a tidal boundary, right down the coast, then you'd use a head time boundary, and you'd manually enter in that time series data set.
Or just you copies from Excel straight into that from the properties.
It's just copy and paste.
Yeah.
And it'll display the values you put in that graph on the right. And it's a very easy way just to quality check that the data you've got is right. Very useful. The next boundary we like to include is an initial water level. This is something which new users often forget, and it's very useful. Okay, so we go through the same process, adding a layer. Here we select initial water level. Pretty obvious. Then we simply draw a polygon over the different regions of our domain where different water levels may exist. So for example, standing water bodies upstream, or more importantly at the downstream of the model, we need to make sure that the initial water value we specify matches the tidal value at the start of our simulation. If you create a model and you find it goes unstable within the first 1 or 2 time steps, I guarantee you've forgotten to set an initial water level that matches that downstream boundary value. And so the model is essentially flooding itself sort of shocking the model with a wave coming through. So don't forget your initial water levels. You can select that polygon and then set that value. There's actually also an option for a global setting underneath job control, 2D model settings, levels. It's the top item there.
So it's just going to cover the whole model as opposed to that area. Okay.
And the regions that we specified previously actually overwrites this value. So often people set this value and then add additional polygons for the standing water bodies like lakes. Okay, upstream inflow. Similar approach to the downstream, although it's just a different layer type. This one's a flow boundary.
So you're adding water to the front of the model.
That's
just
right.
Pushing water on.
This is where the water will come in.
Yeah.
We'll use the polygon feature. Once again, we'll snap that boundary to the active layer and just make sure it's perpendicular to flow. And then you can manually enter in whatever flow items you wish. Just copy and paste from Excel. There's also an additional option in XP where if you're doing a coupled hydraulic model, you can also link flow area boundaries to the hydrograph that originates from your runoff layer. Or alternatively, you can use direct rainfall modelling. We won't touch on that here. I'd recommend viewing the direct rainfall modelling webinar.
Yeah.
There is one.
Yeah, we run a direct rainfall, modelling with direct rainfall. If you just Google that, I'm sure XP will show up. So you can watch all about that, but we're just keeping it simple here, just for the 101-ness and in the interest of time.
Mm-hmm.
But there's all sorts of methods that you can choose for bringing your... We even go through the traditional methods in that webinar, I believe, too. So do look out for those.
Okay, so the final element was your 1D culverts. Very quickly, so the editing tool for 1D items is in the top right. Having entered in your culvert dimensions and inverts, to link that to the 2D is as simple as selecting link invert to 2D and then setting the invert of the culvert and then also a spill crest level. Now the spill crest level is just a hypothetical value which will be above the water surface in the 2D. So just set to some number which is well above that.
So I've got a question. We get this all the time. There's two options there, link invert or link spill crest. So link inverts for culverts. For
culverts through embankments.
Yep.
Yep.
And so spill crest would be for...
That's your underground pipe network.
Okay, so like a manhole or a pit.
Exactly.
Yeah, okay.
Yeah.
Cool. You just tick that box.
That's all
and
it
it's
is.
done. Okay.
Okay, so that's it. That's all the inputs we need. So now it's just a matter of setting our simulation controls. Now I'll rush through this in the interest of time. Most of this is done up in the job control 2D model settings. And you'll see a window such as this. And there's a variety of options on the left with different items such as general, model output, result types, etc. So under the general tab, to get this model working, make sure that our 2D domain is active. So we select that. You can set a time step here, but we've already overwritten that elsewhere in our domain layer. We've already set the land use category to pasture. We'll leave that as is. And then we'll just set this to inactive. This is an area type, and it sets the default area type for the whole model. And we've then overwritten that with the active polygon. So that's the preferred approach. So I recommend you just familiarise yourself with these job controls. So here we have the model outputs, where you can set the regularity of your output interval. Different result types. We've just selected velocity, water depth, and elevation, but there's a whole range of options. The next one that I really like to mention is projection. So I'll show you how to export our results to GIS. Before doing that, though, it's important that you set a projection here, and XP will use that projection for all of the exporting. So it's very convenient just to load from a map info file. Also, because we've used the DTM builder, it's important to select use DTM for that topography. You can also import external data sets if necessary. Then we want to set the start and end time. So that's done under the hydraulic job control. We're running our model for 3 hours. Let's check the solve mode. So one of the strengths of XP is that you can do your hydrology, you can do your hydraulics in the one package. But in this instance, we're just doing hydraulics. So we just want to make sure that we've selected the right mode for the model. And then solve. That's it. So that's all that's required. This window will pop up. You can have a song and dance. You've just created your very first 2D model.
Your jokes are very two-dimensional.
Okay, it doesn't stop there though, so you can have your little quick celebration, but then I really do recommend you look at your results. This is where engineering judgment comes in. Within the XP interface, you'll see there's an item now for 2D results where you can select to view water depth, elevation, velocity, etc. Down the bottom left, you'll have your simulation controls, so you can skip through the time varying results if you're not just looking at the maximum min values. Here's an animation of the model that you'll be able to download. So here you can see we've got water coming in from the inflow at the top of the model. It's passing through the culverts in the road to the west and just filling up the basin. At some point here we'll see the road starting to overtop. So what we're doing here is we're capturing the flow through the culvert as well as over the road in 2D. So the culvert's in 1D and the road's being represented in 2D. And XP will automatically assess the hydraulic behaviour to determine if that topography should be applied using a weir function. Previously, it's a very simple process. It's a matter of just selecting the result dataset you wish to export, choosing export results, setting a file path. And there's a variety of options there. You can export it to a GIS file. Here I'll be exporting it to an Esri grid file at a 2 meter cell resolution. So lots of available options within that output file format.
I believe we're looking to add some more in the future as well.
Mm-hmm.
But you've got your generic ones there that most packages use, so that's good.
Okay, tips and tricks. I'll just quickly brush on some common, I guess, user errors that we find. The first one is rubbish in, rubbish out. When it comes to input data sets, definitely check them. If the quality of your topography data is very poor, then your results are going to be poor. And that comes with all of your data sets. Check your quality. The second one is model time step. Many people don't know what time step to use. As a rule of thumb, if you're working with metric units, the time step should be around half to one fifth of your cell size. So if you're modeling at a 10 meter resolution, your target time step should be 5 to 2 seconds. Now, XP will run at smaller time steps than that, but for very little advantage. Number one, your model will take longer to run. Number two, often it can actually hide issues with your topography data that would otherwise send a model unstable. So if you work within those bounds, that's usually the recommended approach.
Yeah, so you don't want to capture water every centimetre running down a 1 metre plane. You really just want to capture it there. You don't need to go the whole way.
One of the strengths of the solution scheme that XP uses is that it's an implicit scheme. So it actually uses matrix calculations to step forward in time. So it's much more efficient than the explicit schemes that other solvers use. Okay, so let's look at model resolution. This actually ties in with the time step a little bit. What should you use? As a starting point, I recommend just put some thought into considering what you're trying to model. Make sure that your model adequately represents the key topographic features.
So if you've got a road's what, 5 metres, 6 metres wide typically. If you want to capture that road, make sure your grid isn't above that, otherwise you're not going to capture the road curve.
Exactly.
You're going to miss it. So you just got to think about what you want in the model. And you start big and you run an analysis to see where the water's falling quickly, and then you can refine it later.
Absolutely, yeah. I often find it's better to start big and then work down, sort of sensitivity test style approach.
Yeah.
See how that refined resolution changes your results. If it's not changing things dramatically in your area of interest, then all you're doing is increasing your run times unnecessarily.
A question I get a lot is how fine can you go? And the answer is how fine is your data? It all comes down to the underlying data set. You're not going to get more resolution if you've only got a 1 metre grid data underneath in terms of your LiDAR or your survey information. If you go finer than that, you're just wasting time. So it all comes down to how fine that data is. And you can go as fine as you like. It just comes down to model run times, really.
Typically, I'd say probably half a metre is as fine as most people would go.
Yeah.
As a general comment here, when I see new users, they often feel they need to go finer than what they do in reality. So sensitivity testing is a good way to get a sense of what's appropriate. But then also we need to consider runtime. If you double the resolution by halving the cell size, that actually increases your runtime by a factor of 8. Now the reason for that is doubling your resolution will increase the number of cells by 4. So the number of calculations increase by 4. But if you remember that ratio in time step to cell size, that also means you have to halve your time step. So it's 8 times the number of calculations for a halving in cell size. So if you'll find you've got an unwieldy model that takes a day to run at 1 metre resolution, increase that resolution to 2 metres, which will still be a really fine model, and all of a sudden you'll have run times that are acceptable.
4 hours as opposed
to a couple of hours.
Yeah.
The final item here is model health. So it's okay to run a model, but you really need to make sure that it's given the right answers. We're very fortunate that we've got a tool that is very accurate as long as it's being used properly. Here I always recommend to calibrate to historic data if it's available. That's time and time again the best way to reduce uncertainty in your assessments. Do a common sense check. The number of times that people do their model and then just walk away from it without looking at the results with a critical mind astounds me. So make sure you look at results with a critical mind. If there's a road embankment that you know should overtop at a certain level, check that it is. And finally, something that's very good in the XP interface is the simulation analysis tool. So if you go to the top of the interface, you'll see the analysis button, and then there's also the 2D simulation summary. Here there's a variety of graphs that you can use to verify that your model is healthy. So here we've selected the cumulative mass error. What you should be aiming for here is less than plus or minus 1% at the peak of your event. On warm-up, as in this case, we're seeing the mass error down around 3%, but then once you're getting towards the peak of your event where you're most interested in the results, and it's not just wetting and drying, then the mass error is quite good. Common ways to fix mass error: using a time step that's too high. Reducing that time step down to that range that we recommended will do wonders. Similarly, your inflow and outflow boundaries, if those aren't digitised perpendicular to flow, it can introduce some mass error. So just correcting those things are a really good piece of advice.
So thanks everyone for joining the webinar. There's a lot of questions to get through, so we're just not going to have time to cover them all today. We will write to these questioners and get you your answers from the webinar. No question goes unanswered here at XP, so we will answer those. Look out for the webinar recording. We'll load the model up as well, and instructions to download the evaluation copy so you can actually go through this yourself and be skilled up to use 2D in the future when you want to. Any other questions, by all means, send them to the email address on the screen. And thank you very much for joining again our record webinar. Very happy about that, and we wouldn't be able to do it without everyone joining. So thank you very much, and see you at the next webinar.